assignments, doubts, exams. We have got you back. EduPlanner make every chapter easy to understand. Stay tuned, learn more, grow with us.
So for this problem, we are given the equation CH4 gas plus CO2 gas reversibly reacts to form 2CO gas plus 2H2 gas. And we have a Kp of 45 times 10 to the second at 825 Kelvin. And so what we want to do here is the first thing we should do is find the number of moles of our reactants. And so we're given that we have 22.3 kilograms of CH4. So we can first convert that to grams. 1 kilogram is 1,000 grams. And then use the molar mass of CH4, 16.04, to convert it into moles. And so now we have 1390.3 moles of CH4 or methane. And we can do the same thing with our CO2. We start out with 55.4 kilograms of CO2. We convert it into grams and then use the molar mass, which in this case is 44.01 grams per mole, and that gives us that we have 1258.8 moles of CO2. And so since we're given a Kp and we're told to treat this as an ideal gas, we can convert each of those into partial pressures. And so for CH4, we can use the ideal gas law, P equals nRT over V, plug in our values, 1390.3 times 0.0821 times 825, our temperature, and then divided by our volume, 85 liters, and that gives us a partial pressure of 1107.3 atmospheres. Now we can do the same thing for CO2. P equals nRT over V. Our N this time is 1258.8 multiplied by our R value and our temperature, and then divided by 85 liters, and that gives us a partial pressure of 1002.6 atmospheres. So now that we have that, we can set up our ice table, which I'll do on this page. So initial change equilibrium of our pressures. And so we have these pressures here. Our reactants, CH4 and CO2, and our products, CO and H2, and then our initial change and equilibrium. So we have 1107.3, 1002.6, and then these both start at 0. We are losing x here, and we're gaining 2x here because of the ratio, the molar ratios. And so that gives us an equilibrium of 1107.3 minus x for CH4, 1002.6 minus x for CO2, and then 2x for both H2 and CO. So now we want to move into our Kp equation. So Kp is equal to the P of CO squared, the P of H2 squared, over the P of CH4 and the P of CO2. And so that's going to end up being 2x squared times 2x squared over 1107.3 minus x, 1002.6 minus x. And that equals our Kp, which is 45 times 10 to the second. And so what we want to do here now is an algebraic trick, and since these x's are going to end up being so small, we can call them essentially 0 or insignificant, which gives us a much easier equation to solve, which is as follows. 16x to the fourth. And so when we solve this, we get an x value of 74.75. And so now that we know our partial pressure of H2 at equilibrium is just 2x, so 2 times 74.75, which is 149.5. So now that we have our partial pressure of H2, we can use the ideal gas law again to find our number of moles and then eventually our number of grams. And so we plug in all our values, 149.5, 85 liters over our R value times our temperature. And when we do this, we get that we have 187.7 moles of H2. We can convert that to grams by multiplying by the molar mass of H2, 2.02 grams per mole. And so we now know that we have 379.19 grams of H2. So that is one of the questions that's asked. Another question that is asked is, what is our percent yield in this case? And so our theoretical yield would be if we used up all of our limiting reactant. And so our limiting reactant was our 1258.8 moles of CO2. So if we used all of that up, we have a 1 mole of CO2 to 2 moles of H2 molar ratio. So we just multiply that number by 2. And when we do that, we get 2517.6 moles of H2. And so now I'll go to a new page again, and now we just take our actual moles of H2, which was 187.7, and we divide that by our theoretical moles, which is our 2517.6. And when we do that, we find out that we have and then actually here I will erase some of those. We have to multiply it by 100 to get it into a percent, and that gives us 7.5% yield. So that's the answer to the second part of the question.